This demonstration presents the end-to-end federated AI workflow in Trustee, from retrieval and secondary use of data from external data spaces to secure global model collaboration. The Trustee personas that participate in this scenario are developer, model provider, FL prosumer, and model consumer. The scenario originates in the automotive domain, where cross-view geolocalization, CVGL, requires high-quality satellite imagery paired with ground-level data. Pairing GNSS coordinates with appropriate satellite tiles is complex, and access to high-resolution imagery is often restricted or costly. Trustee addresses this challenge by integrating directly with the Copernicus Earth observation data space, enabling the retrieval of satellite images based on GNSS coordinates and acquisition date filtering. While current spatial resolution constraints of Copernicus satellite images may limit certain high-precision applications, Trustee demonstrates architectural readiness for seamless integration of Copernicus data and other third-party sources within modular CVGL workflows. In this demonstration, 3 sequential stages are showcased: external satellite data acquisition via Trustee's Copernicus connector, registration of locally trained AI models as part of Trustee's distributed model sources under governance and compliance frameworks, execution of a federated learning process where encrypted model parameters are securely aggregated to produce a global model. Throughout the process, raw datasets and local models remain at the provider's premises. Only encrypted model parameters participate in aggregation. The resulting global model is stored in Trustee's data lake and made available for authorized reuse. The process starts with external satellite data acquisition via the Trustee Copernicus connector.
This is a demonstration of Trustee developer flow using Copernicus Connector SDK. Developer persona is one of the defined personas related to the Trustee platform that wants to use parts of Trustee platform to develop their own applications, tools, or services. The Copernicus connector is one of the 3 external connectors developed within Trustee project. It has a lightweight interface that simplifies access to Copernicus Earth observation data. It transforms complex, multi-step data retrieval and processing workflows into a single, developer-friendly API calls. Developers typically start the process by accessing the Trustee Developer Handbook, a repository of materials providing useful information that can advance someone's knowledge and understanding of the Trustee platform and technical ecosystem. Tutorials available within the handbook include step-by-step guides that cover key tasks and operations, as well as common problems, and typically involve a guide through specific examples. One of them is a tutorial that explains how to use the Copernicus Connector API covering authentication, session handling, request headers, and usage options via Swagger UI or programmatic access. The Copernicus Connector supports 2 main usage modes. Developer can use the built-in Swagger interface to test the Copernicus connector without writing any code. It's useful for exploring endpoints and checking responses. Developer can also use the API in your own applications by sending HTTP requests or generating an SDK from the OpenAPI specification. We will demonstrate both cases. First, we will show how developers can use Build in Swagger UI tool. Developer opens link to Copernicus Connector API Swagger tool and gets redirected to the Trustee Authentication Manager. After login, the developer can access the tool. First, developer needs to set Copernicus Connector API key and then keys or credentials for accessing Copernicus services, which should be obtained previously in a separate registration process for designated Copernicus service after accepting the terms of use. The API supports access to detailed solar radiation data, multi-level cloud cover, air temperature, solar position, and high-resolution Sentinel-2 satellite imagery, including RGB bands and true color, for Europe, enabling both data retrieval and visualization. For example, developer can obtain list of hourly surface net solar radiation on clear sky, the amount of solar, shortwave, radiation reaching the surface of the Earth minus the amount reflected by the Earth's surface. Developer enters required parameters and after few moments, obtains the data from Copernicus Climate Change Service, C3S. Developer can access Copernicus Connector API also programmatically using tools like Postman Lightweight Client. It can use curl example from Swagger tool and simply copy-paste it in the Postman Lightweight API client. In the example, developer first sets proper CDS API key and then retrieves solar radiation data through Postman client. Finally, we are going to demonstrate how developer can generate SDK in any programming language and use it in their own application, tool, or service. Instructions are also provided in the Trustee Developer Handbook. Developer can use OpenAPI Generator tool that allows generation of API client libraries, SDK generation, server stubs, documentation, and configuration files automatically given an OpenAPI specification in over 50 programming languages and frameworks, including Python, Java, C++, Scala, and many more. There are two main steps. The first one is to download the OpenAPI specification and then to generate the API client using OpenAPI Generator through Docker. First, developer downloads OpenAPI specification of Copernicus Connector. It needs to log in via Trustee Authentication Manager and then download the specification to a local file. Next, we run single Docker command to generate SDK in any language. In this case, we use Python. We set input file with specification, select output location and SDK language. In the folder on the right, we can see the generated files. Developer can start by opening README file with getting started instructions, API description, and examples. There are example usage for every API endpoint. Here you can see the example of how to set CDS API key in the session using generated SDK, following by an example of using SDK to obtain solar radiation data. Here is an example of a simple Python application that uses generated SDK. Of course, some things need to be properly configured, like hosts, keys, request headers, and similar, as described in provided tutorial. In this example, application first sets CDS API key and then fetches list of hourly surface net solar radiation data for Zagreb area in certain period of time. Developers can use Copernicus data and the SDK to build applications, tools, or services, provided they comply with the specific Copernicus dataset's terms of use.
After model registration, the model is discoverable through Trustee, and an FL prosumer may use it and initiate a federated training session to collaboratively build a global model. The user clicks the Login button on the main Trustee dashboard login page. The user chooses Load Another Identity and selects the identity that was provided. A QR code can be used for SSI wallet authentication, or the user can authenticate directly via an organization, such as TechHub, Inc. In the dashboard, the user checks the endpoint information under the Account section. It is required to deploy local Trustee modules for secure storage and encryption before registering a model. Next, the user navigates to ML Provider under the AIMAAS menu, clicks Start Here, and selects the relevant domain, such as the automotive domain. The user enters the credential ID, which is uniquely linked to the model's encrypted metadata, and provides a model name to be used during federated learning scenarios. After submitting the provider information, the user must perform a mandatory, trustworthy AI assessment before creating the agreement, so the user clicks to begin. In the assessment window, the user selects the model provider project type and chooses a template, such as Automotive Pilot. The user must provide the provider ID. They can retrieve this information by switching back to the Trustee Dashboard tab, copying the provider ID token and pasting it into the assessment form. The user gives a name and description and then saves it to continue with the assessment procedure. To begin, the user clicks the Begin button and initially completes the overall framework tests by answering the compliance and design questions and submitting the results. This questionnaire-based assessment is a qualitative, evidence-based software tool designed for self-assessment. It allows the AI developer to perform a trustworthiness analysis during the AI design and development lifecycle. Moving to data management, the user completes the fairness test, addressing prompts regarding bias, diversity, and impact assessments. Next, the user completes the privacy test to confirm privacy by design measures and federated learning usage. Under Algorithm, the user completes the robustness tests to verify safety, auditing capabilities, and resilience against attacks. The user then proceeds to the security tests, confirming vulnerability assessments and data protection measures. Finally, under verification and validation, the user completes the explainability tests to validate the model's transparency. Once all tests are completed, the user closes the assessment project and confirms the closure to finalize and save the data. Returning to the main Trustee dashboard, the user refreshes the page. The assessment now shows as completed, and the user clicks Continue. The user then fills out the agreement details, names the agreement, applies the appropriate license, and sets a start date. The user sets the end date, geographic restrictions, target audience, and the desired platform confidentiality level. The user briefly describes how the model contributes to societal well-being, sets its intended use, and agrees to the traceability and accountability terms. The user clicks Finish and confirms the agreement. Reaching the final report screen indicates the model is successfully registered. Once local datasets are enriched and models are trained externally, the next step is secure model registration within Trustee.
An FL consumer logs into the Trustee platform. The user must have registered the endpoint of the model consumer endpoint where the HE aggregations will take place. The user then navigates to the model prosumer workflow of the AIMAASG UI to begin a new task. The user inputs search filters. Each domain has its predefined filters. For example, in the automotive domain, we assign specific values for the filters such as name and application type. To support a greener approach, past searches can be utilized, saving energy on redundant querying. A new search triggers the Trustee SSIHE process. The system requests encrypted attributes from providers, encrypts target values using their public keys, and compares pairs to validate matches. Finally, we obtain a list of models that match the defined search criteria. Next, we choose the type of computation to perform on the encrypted domain. 3 computations are supported: a simple mean average, a weighted average, and an extended computational method that implements the XAI by design principle. During model selection, past global models can be utilized, eliminating the need for some extra federated learning rounds. The user has selected weighted averaging and has configured the process to run for exactly 3 federated learning rounds. The process enters execution. Terminal windows display real-time logs of encrypted communication and model aggregation. In the background, a federated learning request is sent to the Trustee Federated Learning module. This module communicates with distributed FL clients, instructing them to start the training procedure. Each FL client interacts with its corresponding Trustee model provider to generate private keys. Once the keys are created and securely shared with local model providers, the core FL process begins. Each client trains its local model, encrypts it using its private key, and sends the encrypted model to the Homomorphic Encryption Data Fusion (HEDF) component for aggregation. After aggregation, the global model is stored in the data lake and distributed back to the FL clients to start the next round of federated learning. The workflow concludes successfully and the final status changes to finished. The user can download the generated FL global model.